Okay, so here's the solutions to the first three problems that we were working on last time. So the first problem, when you plugged in x equals 4, you got you got 0 over 0, which is indeterminate. And so we factored the numerator and the denominator and canceled out the common factor. And then once we did that, we just plugged in x equals 4 into the simplified expression, and I got 3/7. Hopefully I did that right. The second problem, if you plug in x equals 1, you get the number. You get a number 2, so that's your final answer. You don't have to do any factoring. And then the third problem is indeterminate. The denominator was a third order polynomial, but we know that one of the factors, because it was indeterminate, we know one of the factors is x minus 3, so I used synthetic division to divide by using x equals 3 as a solution, and you see that it does come out to be 0, which means that it is, that's why we get a 0 in the denominator. So if you factor the numerator and the denominator, you get that, the common factor being x minus 3, so those cancel out. So these cancel out, and then you just plug the number into the second part. So x equals 3 here and there, and I got 2/9. Anybody have any questions on any of that? Okay, now we're going to go back and work on the rationalization here in a second, but before we do that, let's go back to the notes from section 3 to look at the trig, a couple of trig problems, and then we'll. So let's see. So I save the notes from every year. The date that I save them gives me an idea of how I'm going relative to previous years. So anyway, we're pretty much on target. It's early in the semester, but okay. Oh, wrong section. Chapter 3, section 3, there we go. So we had the two squeeze theorem results. We proved one of them, which is this one, by using this unit, well, not unit circle, but a circle of radius b, and making 3 triangles, well, 2 triangles and a sector of a circle. And you can do the same thing. I'm not sure exactly how to do that one. I can't remember how to do that one, but similar kind of an arrangement. So basically what you have to do when you have these trig limit problems is to try to rewrite them as involving sine x over x or 1 minus cosine x over x. So sometimes you have to use trig identities. First thing you do, though, is see whether it's indeterminate or not. So just like we've been doing. So if I plug in the tangent of 0 and I square it and I divide by 0, that's the tangent of 0 is 0, so you get 0 squared over 0, which is 0 over 0. So it is indeterminate. Okay. Now here's a word of warning. Sometimes on the test, when you see it, if you ever see a limit involving a trig function that involves something other than x equals 0, you just plug the number in and you get the answer. So some people get confused and try to use try to convert it into using the trig identity, I mean not the trig identities, but the squeeze theorem. But the first thing you should do is, the only place the squeeze theorem applies is at x equals 0. So if it doesn't equal x equals, or it doesn't approach 0, then you should say, oh, he's trying to trick me. Okay, so let's think about this. So we have to get it in terms of sine and cosine somehow or another. So one way would be to rewrite the tangent as in terms of sine and cosine and see whether there's anything we can do there. We could maybe use one of the Pythagorean identities, but I think the easiest one probably to try out here is to replace the sine, the tangent with the sine over the cosine, and then see how that does. So you can see that I could take one of these sines and group it with the x. So let's do that, see what happens. So I'll have the sine of x divided by x. So I'm going to take one of those, and that, what that leaves me left is the sine of x divided by the cosine of x squared. Now, yeah, or cosine squared of x is the same thing. So let's see if that helps. So we know from the squeeze theorem that that equals 1. And then we would plug in x equals 0. So we'd have the sine of 0 divided by the cosine of 0 squared. And the sine of 0 is 0, and the cosine of 0 is 1. So now it's not indeterminate anymore. So now that it's determinate, the answer is 0, which is still fine. That's an answer. So don't just because you get 0, it's when you get 0 over 0 that's the problem. It's not just 0. 0 is fine. Not sure why that's there. I think that was to show you what to do for that one problem. Oh, let's try again here. Delete that page. Oh, okay, so that's it. Okay, so go ahead and continue on your paper. I will go back to one of the rationalization examples just in case you didn't write that down. So you can start doing those and then so I guess that's good enough one to put up there. I've got a handout. I'll hand out while you start finishing up working on that handout. Did you bring in the handout? No. Okay. So a lot of you guys have already gotten close to finishing the rationalization stuff, which is good. So my wife said she saw you.
Yeah, I saw
Yeah.
it right after I left class.
Yeah. Are you working today? Yeah. She's going to yoga today. So, as I said, for some reason I picked out 1/6 all the time, or at least that's the answer. So hopefully you got that. So we chose square root of x plus 5 plus 3 instead of minus 3. And first thing I did was I determined that it was indeterminate. And then once you simplify the numerator, you should be able to cancel out the x minus 4 in the denominator. With the x minus 4 in the numerator, simplifies down to this. And then you just plug x equals 4. And you get that. So I'll let you work on the other one. You're stuck on that one, huh? The thing about the squeeze theorem is that it doesn't matter what the argument of the trig function is, as long as you divide by the same argument. So even though the squeeze theorem is the sine of x over x, you could have the sine of a over a, or the sine of 200 over 200, or the sine of x squared over x squared. So it's even though it's because this argument is squared that you just have to have that in the denominator. So the answer is 1. Because what you could do is you could say, y equals x squared. Then it would be the sine of y over y. And when x is 0, it'd be 0 squared. You could make that substitution. if you wanted to look at it and make it fit exactly into the squeeze theorem. Or you can just remember that anytime if you have this, the argument of the trig function matching what's in the denominator, then it simplifies down to the squeeze theorem. Okay. Yeah, so let me just give you a little. So the the sine of x over x, that's the squeeze theorem. But it turns out, if I did the limit of the sine of y over y as y goes to 0, that's equal to 1, obviously. The limit as x goes to 0 of the sine of x cubed divided by x cubed is 1 also. And that's because you can always say y, you could say y is equal to x cubed. So by making this substitution, it becomes that, which we already know is 1. So the limit as x goes to 0 of the sine of bananas divided by bananas equals 1. Whatever the argument is, if you have the denominator the same as the argument of the trig function, it's always 1. Now if you had so that's the problem that you have, you'll see in your paper. If you had something like the limit as x goes to 0 of x, actually what would I have? The sine of x squared divided by x cubed, then you could break it up into two parts. The limit as x goes to 0 of the sine of x squared over x squared, which is 1, times the limit as x goes to 0 of 1 over x, which is undefined. So this would be, it wouldn't be indeterminate. The original one would be indeterminate because you'd have the sine of 0 over 0 cubed, which is still 0 over 0. But here you end up with 1 times undefined, basically, which is undefined. Okay. Okay, so there's the solution to the next rationalization problem, 1/6. So we multiply it by 3 plus the square root of 16 minus x in the numerator and the denominator. What that does is makes the numerator into x minus 7, which cancels out with the x minus 7 in the denominator. That just leaves this part, and then you plug in x equals 7 into the answer. We just talked about this one. I think what the book does is they would make the substitution y equals x squared. So when x equals 0, y equals 0 squared, which is 0. So then you would rewrite it in terms of y. Take the limit as y goes to 0 of the sine of y divided by y. And then you can use the squeeze theorem using the variable y, and you get 1. But the reality is anytime the numerator, the argument of the sine function is equal to the, oh yes, so that's the next one. So what did anybody get an answer there for the next one? Let me write it down first. The limit as, I just realized, did I push the record button or not? Yeah, I did. Okay, good. Okay, so the limit as x goes to 0, sine squared of x over x squared equals, anybody get an answer? No? Yes. 1. And how did you do that? Say that again, I missed the first part.
I said the limit of as x approaches 0 of sine of x over x equals 1.
Yes.
And then I just raised both sides to the second.
Okay. Yeah. So one thing I have to remember is that the sine squared of x is the sine of x squared. So you have, this is the sine of x quantity squared. When we get into integration, recognizing that is critical. You know, we have this shortened version. We get used to things like sine squared plus cosine squared equals 1, and then we forget what it really means. And this is just a shorthand version of this. It allows us to get rid of the parentheses. But when you actually do the mathematics, the calculations, it makes a lot of sense sometimes to just rewrite it in this form. And so what you can do is you can take one of the sines from the sine squared. So that's what, okay. I know his name here. Where is it? Evan. Yeah, sorry, Evan. I knew it started with an E. I couldn't pull it out of my brain. Okay, so limit as x goes to 0 of the sine of x over x. So what you do is you break it up into two things that are using the squeeze theorem, and each one of those is 1. I think what you were saying was you took this and squared it or something like that, which is the same thing, but so you get 1. And how about the last one? Anybody besides Evan? What'd you get on the last problem? How about Maya? What's that? I haven't done that one yet. Okay. I'll let you guys think about it. So just try to rewrite it as, what you want to do is you want to try to make it into something like one of these examples that we did here. You just have to make it so that the denominator has the same argument as the argument of the sine function. But you can't just make it. Math doesn't allow you to just make things. That you've got to actually maintain an equality to be able to do that. So yesterday we drove to Danville. My wife's friend from college was celebrating her 60th birthday, and she works for Big Brothers and Big Sisters, as well as she's a minister of a church. And it's funny because she tells a story. She's about as tall, same height as my wife, and she's black, and she was in our wedding. And back in the 70s, that was kind of a little unusual, And she was telling this story. She says, "Yeah, I went to Winchester to be in Martha's wedding, and every time I used a towel, Martha's mother washed it." But now I don't remember that happening, but it's just because so the other sad thing about that time was Martha's grandparents came to visit, before the wedding, and Pat was helping out washing dishes in the kitchen, and they assumed that she was there as a hired person instead of being in the wedding. It's kind of pathetic, but that was, that's your grandparents, actually, probably your great-grandparents. That was kind of their mindset at the time. So she had this story about me. When at Virginia Tech, there was two dorms. Well, there's more than two dorms. There's two dorms. One called East Ambler Johnson and West Ambler Johnson. And East Ambler Johnson was the guys' dorm, but it was at that time there were two dorms that were no visitation. So you had the guys with no visitation, and you had the girls with no visitation. But the girls, the first two floors you could have visitation on weekends. The extent of visitation was that you could go from 8 o'clock in the morning on Saturday to 11 o'clock at night, and then you had to leave, and then you could go from 8 till 11 on Sunday. But the other door, the third through fourth floor, was no visitation, no opposite sex visitation. And so they used to call the upper floors of West Ambler Johnson the Virgin Vault. Okay. And when Martha, she was on the first floor of Ambler Johnson her freshman year, but she was an RA, resident advisor, her sophomore and junior years, and it was in the upper floors at Ambler Johnson, and Pat was on the floors. And so the only way I could see Martha during when she was, I had moved off campus, was to go to Ambler Johnson. In between the two buildings, there were lobbies at each floor. So I would go to the lobby waiting for Martha. And I was apparently, I don't remember this, but this is her story. She said, "I saw Stephen in the lobby, and he looked very distraught. And I thought something had happened between him and Martha." And so she says, "Stephen, what's the matter? You look sad." And she said, "I don't want to talk about it." And then so she went up to Martha's floor and said, "Hey, Stephen's on the third floor lobby, but something seems to be bothering him." So anyway, she went and asked, and so she came back, and Martha said, "Yeah, he was distraught because he got a B." That was I don't remember. I don't think I was that psycho about the whole thing, but that's what she remembers. So maybe it's true. I don't know. But, so it wasn't a relationship problem. It was getting a B. Okay. Does anybody have the answer for the last one now? How about Cassie? Okay, I'm gonna help you work through this problem. So the limit as x goes to 0 of the sine of 2x divided by x. So I was saying that the argument of the trig function, well, what is the argument of the trig function? Two x, right? Yeah. So if this here is exactly the same as the argument of the trig function, then I should be able to use the squeeze theorem. Okay? But I can't just add a 2 to there. So what do I need to do as well? If I divide by 2, I need to multiply by 2. Yeah. So you could then break this up into the limit as x goes to 0 of 2, or 1 over 2. No, 2. Yeah, 2. Times the limit as x goes to 0 of the sine of 2x divided by 2x. And, you know, I could let 2x equal y and change that to y, or I can just say, Dr. Nicholson said, as long as the argument of the trig function is the same as the denominator, the squeeze theorem works. So this becomes 1, and the limit of a constant is just the constant because it doesn't involve x, so it's just 2. So the answer is 2. Okay. And let's just prove that by plotting it. So let me, so if we go to the graphing function here, problem, graphing thing, and we plot the sine of 2x divided by x, and I graph it, and we're looking for the limit as x goes to 0, and you can see that when x equals 0, that y equals 2. And again, there is an indeterminacy there. You can't see it because it's just one point, and there are an infinite number of points. So if I were to change this to 3x over sine of 3x over 3, then it becomes 3. But if I do the sine of 3x over 3x, put that in, and it just becomes 1 again. And that's the only point that this function is indeterminate, is there. Okay, so you guys can turn those in after class is over. Yeah. So I think we're done on section. Oh, the handout I gave you. So let me pull that up so we can look at it on the screen. There's two sides to it. One that I think says one-sided limits, one that so I have to look at it because I forgot which one side's which. Just to remind you, all these handouts are in Blackboard if you miss class or something. Sometimes it's easier for me to find this on Blackboard than it is. So this is okay. Now the question is, can I rotate this? Oh well. You have it. You have it. Okay, so here we go. So it says flowchart for evaluation, one-sided limits, the other side's flowchart for evaluation of limits. So you start at the top, you have some limit you're supposed to be evaluating. The limit of the function f of x as x approaches c is something. So the first thing you do is you plug the number into the function. And you can get, there's three possibilities. One is you get a number, like the second one on our handout. The middle one is it's indeterminate. Depending upon what the form of the function is, you do one of four things. And you get plus or minus infinity, or it's undefined. If it's undefined, then the limit does not exist. So you get a limit, plugging it in, you might get indeterminate, or you get does not exist. Now the four things that can happen is if you have a ratio of polynomials, you use the dividing out technique. If there's a square root involved, you use the rationalization. If it's a trig function, you use the squeeze theorem. And the last case is this absolute value of x minus c over x minus c. And in that case, the limit just does not exist because it has that stepwise behavior. It's not, does not, above it doesn't exist because the limit is without bounds, whereas in this case, it's just that as you approach x equals c from each side, you approach either positive 1 or negative 1. So, and I let you bring that into the test, so you can use that in addition to your cheat sheet. Now, there's one thing we skip. I don't know if it's in this section or the next section. Let me just. There is a more formal way of looking at limits, and it must be in the next section or the final section. Yeah. If you ever become a math major, you probably will be exposed to this. I don't even see it, but it's called the delta epsilon method, and I skip it, and other people that I've talked to who teach calculus have skipped it as well, because I mean, up to this point it seems pretty straightforward. It's not that complicated to do limits. The delta epsilon formal approach at proving limits is not straightforward, and it tends to confuse people, and then people are like, oh, calculus is so hard, I don't understand it. And it's really not that important for understanding calculus, so I just decide not to do it. I don't think I quite understand it either, so I'm just... Okay, so we got two more sections in chapter 1. We've got the definition of what continuity is and talk about one-sided limits. So what we've done so far is two-sided limits. We approach x equals some value from both sides, from the left-hand side and the right-hand side, and we look to see whether it approaches the same y value. One-sided limits are if you only approach from the positive side or the negative side, or the right or left side. Now, before we talk about continuity, I just want to talk about what is discontinuity. It's easier to... So there are three possible types of discontinuities at some point. One is the function is not defined at x equals c. So that's kind of that's the example that we have with the indeterminate result. So you have, so it doesn't exist or is not defined at x equals c. Because it's indeterminate is one case. Another case is just, it might be a stepwise function where you just decide not to define it at a particular point, but that's a discontinuity. Another example of a discontinuity is the limit does not exist. So that's usually the case of vertical asymptotes. So that you might say the limit equals infinity, but it's not really. It's a case where it approaches infinity, but infinity does not exist. So, and the third case is where the function exists, but the limit exists, but it's not equal to the value of the function. I'm trying to decide if that's actually an example of the indeterminacy. Limit exists. Well, this again could probably be the case of a stepwise, piecewise function. So let's just give three examples of those. So, well, actually, this is the example of the second case. The limit of the function does not exist at x equals c. So if you have the function y equals 1 over x minus c, if I asked you to find the limit as x approaches c of 1 over x minus c, we'd say, what is the limit? We'd say it does not exist. So that's the limit, but in terms of discontinuity, the reason it's discontinuous is because if I took my cursor and I follow the function as I approach x equals c from the left-hand side, it goes to negative infinity, and then right on the other side of the value x equals c, it goes all the way up to positive infinity. So one definition of continuity is that you can keep your pen on your graph and you don't ever have to lift it. So as soon as you have to lift your pen when drawing the function, then it becomes discontinuous. If you don't have to lift it, then it's continuous. So you can see that I have to lift my pen from here and take it over to there. The limit of f of x exists at x equals c, but is not equal to f of c. So one example of that would be if I had a straight line and then I had a hole for some reason, and then I have another straight line that continues on, and I decide to define the function at x equals c as some other value. So let's say this is 1 and this is 2. So the way you would do this is you come up with some kind of linear function, or you could have a linear function multiplied and divided by x minus c. So you get a hole, and instead of just leaving a hole there, you'd put a point. So again, if I were thinking about continuity, I'd be keeping my pen on the paper. I'd get here, I'd go up to this point at x equals c, and then I'd come back down here. So I have to lift my pen up twice to move through the entire domain of this function. Now, if you were not defined at x equals c, if I just said it was a hole, then the first case, that would be a case of the first one, where the function is not defined at x equals c. So here's the actual continuity. Let me put this on one page. If we meet the following conditions, then the function is continuous at point x equals c. So it's the opposite of the definitions of discontinuity. So if it's not discontinuous, then it's continuous. So for a function to be continuous at x equals c, the function has to be defined. The limit has to be equal to the value of the function, and the function has to exist. So there are cases where you could come up with something that would satisfy 2 out of 3 of these requirements, but you would still be discontinuous. But if you satisfy all 3 of these requirements, then the function is continuous and you won't have to lift your pen up. Polynomials are continuous. The sine and cosine are continuous. The tangent, the secant, the cosecant, and the cotangent are not continuous because there are points where the function is not defined at the vertical asymptotes. Rational functions are continuous except at vertical asymptotes. The logarithm and exponential functions are continuous. So most functions are continuous. There's just a few special cases where the function is not continuous. I usually require you to know what this is. A few things that I ask you to memorize. One of them is this: what are the conditions under which what conditions have to be met for the function to be continuous? And those are it. So I've already talked about this. Physically, you just don't lift your pen. If you don't lift your pencil, then the function is continuous. Now, there are some discontinuities, meaning places where it's not continuous, where you can remove that discontinuity by doing something, by redefining the function. So this is an example of a function where you have a discontinuity because the function does not exist at x equals 2. It's a whole. So the question is, how would you rewrite this function so that it is continuous? So let's add a page here. So we'll say this function, which I'll define here, f of x equals, and it's already in factored form, so you can see why it's discontinuous because of the so the function such is discontinuous at x equals 2. To remove the discontinuity, okay, so what we're going to do is we're going to make f of x this. So f of x equals x minus 2 times x minus 3 divided by x minus 2 for the domain from negative infinity to 2. We're going to make it equal to, so this is, and at x equals 2, we're going to let it be equal to, if we canceled out these terms, like we would do in the canceling out technique, you would end up with just x minus 3. So if you plug 2 into this equation, you'll have 2 minus 3, which is equal to negative 1. Okay, so that's what we're going to, so what we'll say is f of x equals negative 1 when x equals 2, and then the function goes back to its normal form for the rest of the domain, which is from 2 to positive infinity. So that's how you remove the discontinuity, is to make it into a 3-part function with the additional requirement that the value of the function at x equals 2 is such that you fill in the hole. So for the first part of the function, we're following this red line. When we get to the normal discontinuity where there's a hole, we put a dot there because we just said at x equals negative 2, at x equals 2, the value of the function is negative 1, and then we continue on. So we're basically just filling in the hole by doing this. So that's how you remove discontinuities. You can do that with functions where you have an indeterminate result and the limit exists. So this function now satisfies all 3 requirements. The 3 requirements are, it initially did not satisfy the requirements because f of c was not defined. And also the limit did not equal f of c. The limit existed. The limit was negative 1, but these 2 requirements were not satisfied. But now that I've put that point there, the value of the function is defined at x equals c. It's equal to negative 1. The limit is equal to the value of the function because I picked this point so that it equaled the limit, and also the limit exists. So this does satisfy all 3 requirements, whereas this does not. So when I ask you to remove a discontinuity, it's going to be of this form, and basically you need to rewrite it as such. Basically you're finding the limit of the function as x approaches 2, and you make that limit equal to the value of the function, and you make sure the whole domain is defined. The other kind of discontinuities are called non-removable discontinuities, and those are the result of the absolute value type function or rational functions where the denominator goes to 0 but the numerator doesn't. So we looked at that just a little while ago. The x minus 1 over x minus 3 was the case of a discontinuity, but it's non-removable because, I can define the function. Here's f of x. So f of x was something like 1 over x minus 3. And again, the three requirements for continuity are that the function exists, which it doesn't. The limit does not equal the value of the function because the function does not exist anyway. And the limit does not, so this case, it pretty much doesn't satisfy any of the requirements for continuity. I could make it, I could define the function here, so I could let it be any value between negative infinity and positive infinity. In that case, the function would be defined, but the limit of this function would not be equal to the value of the function. So you can never make this discontinuous function into a continuous function. There's no way to fill in all the spots between here, basically. So it's the same way with the absolute value function. Let me just add a page here. So if the function f of x is the absolute value of x minus 2 divided by x minus 2, what that looks like is something like this, where this is x equals 2. So from just a qualitative standpoint, I'm drawing along here, and I've got to lift my pen up and go up to all the way up to there. So it's discontinuous. The reason the function does not exist at x equals 2. It's indeterminate. Also, the limit does not exist, so you can't say the value of the function equals the limit. So this probably doesn't satisfy any of the requirements of continuity. And again, there's no point that you can put in here that would make this discontinuous function transform into a continuous function. So this is the second kind of non-removable discontinuities. Okay, so that's it for continuity. One-sided limits, it's really just like two-sided limits as far as evaluating them. You can look on the other, if you turn your sheet over, flowchart for evaluation of one-sided limits. So says the limit is f of x as x approaches c from the positive side. That means the right-hand side. So what you do is you use this superscript, either positive or negative. The negative means that it's approaching from the left-hand side of c, and the positive means it's approaching from the right-hand side of c. As you can see by the flow chart, evaluating one-sided limits is pretty much the same as evaluating two-sided limits. And for most of the cases, they approach, the limit as you approach from the left-hand side is equal to the limit as you approach from the right-hand side. So we're not really going to be learning a whole lot new as far as technique. The key thing is that, these can be different numbers, just like this absolute value. If I approach x equals, in this case 3, from the left-hand side, the limit does exist, because as I get closer and closer to x equals 3, it looks like the function is going to be -1. Whereas over here, if I approach from the positive side, then the limit is going to approach 1. The function does not exist here, but as we get closer and closer to x equals 3, we're still approaching as close as you get to x equals 3, but not equal to x equals 3, you're going to think that the value is 1. So let's just use that as an example using this terminology. So if I said the limit as x approaches 3, and we use a little plus sign, of the absolute value of x minus 3 divided by x minus 3, that's going to be equal to 1. And the limit as x approaches 3 from the negative side of x minus 3 over x minus absolute value of x minus 3 over x minus 3 is equal to negative 1. Now, if you have the case where the left-hand limit, right-hand limit does not equal the left-hand limit, then the actual limit at x equals 3 does not exist. So we can write that out as well. So the actual limit, if I said what's the limit as x approaches 3 without any plus or minus of this ratio of absolute values, what is that? We'd say it does not exist. So the limit does not exist, but the left-hand limit exists and is equal to negative 1, and the right-hand limit exists and it's positive 1. Because these don't equal each other, then the actual limit, which requires you coming from both sides, does not exist. The other big case of where the two-sided limits come into play is vertical asymptotes, and that's what we're going to spend most of our time on. And the question will be, at a vertical asymptote, and we approach from the right-hand side, is it going to positive infinity or is it going to negative infinity? And if you plot the curve, it's obvious which it is, because you can see the curve going up or you can see the curve going down. But we want to be able to figure out, is it going up or is it going down, without plotting the function. Yeah, there's this theorem here. Let's just talk about the theorem. So for a limit to exist, the limit must be the same whether x equals c is approached from the negative or the positive side. So we have this theorem in the book, theorem 1.10, the existence of a limit. So here's the formal way of saying this. The limit of f of x as x approaches c is L, some value, if and only if the left-handed limit equals L and the right-hand limit equals L. So that's how you define what the limit is based on the one-sided limits. It's just another way of defining limit. Now, if I looked at this function, let me add a page here. So I said the case is, the case we're going to be looking at here is these rational functions. And the question is, what is the limit as x approaches, in this case, negative 3, because that's where the denominator will go to 0, from the positive side of this function, and what is the limit as x approaches negative 3 from the negative side of this function? Question mark. Now here there's kind of an exception, because we said the limit of the limit without left or right hand side does not exist. We said two reasons. One was because one went to negative infinity and the other went to positive infinity. We also said infinity does not exist, but we're going to make an exception here. So instead of saying it does not exist, we do want to indicate which direction it's going. So so there's a couple of ways you can do this. You can do it graphically, and if I graphed it, what you would find out is that from the positive side of negative 3, that it goes to positive infinity, and here it goes to negative infinity. If I graphed it, I could do it numerically, and it's 9 o'clock, so we'll stop there. So I haven't given you any new homework to do from this section yet. We'll do that tomorrow. So I usually do watch time. So again, if you ever see me going over, that doesn't happen very often. Make sure to tell me. Make sure you hand in your hand. Make sure you hand in this thing. So the physics lab is open, and we'll see you at 9:15. Yes. Oh, I didn't give you one? There you go.